So, good evening. I'm Calvin Joseph, and today I'm going to present. Today, I'm going to discuss the problem solving and doubt clearing session for the course Electrical Measurement and Electronic Instrumentation, which was taught by Professor Abhishek Chatterjee of IIT Kharagpur. And this is the outline of the things which I'm going to consider. So, I will first talk about what is a digital voltmeter. There's a linear ramp type digital voltmeter is Z, what is the circuit, etc. Then there are certain flaws, there are certain inaccuracies which can occur when we use a linear ramp type digital voltmeter. So how do we overcome those inaccuracies using a dual slope voltmeter? Then I will also consider what is an ADC, what is a DAC, and then we will see some further examples. Okay. So I'll start. Start with week 9. So first we will consider what is a linear ramp type voltmeter. Okay. So basically, what does a voltmeter do? A voltmeter will, good evening. So basically, what does a voltmeter do? A voltmeter will tell you what is a voltage. Yes, you're right, it measures the voltage. So now we studied the various types of instruments which can be used to measure voltage, but now we will see how do we do it using certain electronic circuits. Okay. So suppose we have a comparator is used. A comparator with via an op amp is used, etc. We have let us say this is my voltage Vx, which is unknown, which I want to measure. Okay, this is a voltage Vx, which is unknown. Here is a ramp VR, which I know. Okay, this goes to a comparator. So what will the comparator do? It will go high when VR is greater than Vx, else it will be low. Okay, so let us change the polarity. Minus plus. Okay. This goes to an AND gate. AND gate. Here is a clock, F clock. And this goes to a counter. Okay. This is my counter. So this is a very simple logic which we have. What we must do is, this VR will be a kind of RAM. It will be a kind of RAM. Okay. It will go to some maximum value and it will come back. Now we have Vx. This is my Vx. Okay, Vx. What is this Vy? How will the Vy curve look like? Vy will be high. Okay, Vy will be high. Whenever Vr is less than Vx, whenever Vr is less than Vx, then Vy will be high, else it will be low. Okay, else it will be low. So now, when Vy is high, then we also have one clock. It's coming like this. Continuously the clock is coming. Okay. So this clock is continuously coming and it is incrementing my counter. My counter value is increasing. Initially counter value is 0, then becomes 1, then becomes 2, then becomes 3, 4, 5, 6, etc. It keeps on increasing. Then after this instant, even though your clock is coming, it will remain fixed. It will no more increase. Even though the clock is coming over here, after this instant, it will remain fixed at 6 only. It will not increment any further. Can you tell me why? Hmm? So what is happening is, when Vy is high, then only you are enabling the counter. Else when Vy is low, you're disabling the counter. Even so, okay. So now to the AND gate, you have two inputs. F clock is continuously coming. F clock will be continuously coming. But your Vy will be high for some time, it will be low for some time. So when Vy is high, then only your counter will count. If your Vy is low, your counter will not count. So this Vy is effectively like you're enabled to your counter. Okay. So what happens? Okay. So your counter value is 0. When Vy goes high and your clock signal comes, this is your F clock. It starts incrementing. This is the value of your counter. It goes from 0, goes to 1, 2, 3, 4, 5, 6, etc. It will keep on increasing. Okay. So this is how a counter will work. And how it will increase its value. So there are two things which are important for us. So this ramp, this VR ramp will have a slope. That slope will be some V peak upon some time. Okay. It is something like V peak upon some time. So this slope we must know. Second thing is the counter value must start from 0. It should not start from any other value. So the counter value has to start from 0. And what is this voltage Vx? Now how will we find what is Vx? My Vx will be equal to this slope into how much this time is there, this time t1. And what is this time t1? Into the number of clock cycles, or the counter value, sorry. It is the counter value into the time period of your clock. Okay. And that actually is equal to slope into counter value upon f clock. Okay. So in this manner, we are able to find out, we are able to measure the voltage. Okay. Uh, so any doubts in this, or you want me to repeat it again? Okay, fine. So we have found out. So what could be a problem you might face over here? Can you tell me what could be the issue you might face in such an arrangement? Hmm? Okay, so in this method, yeah, there are two problems which can happen. One is your slope. This slope can change this also can change. Both can vary. So if your slope changes by 1%, your V measured or your Vx will also change by 1%. There will be 1% error. If your clock changes by 1%, how if your clock changes by 1% and your slope is the same, then what will be the error in V measure? What will be the error? So the error will again be 1%. Okay. Whether it's in the numerator or denominator doesn't make an issue. We have studied relative errors and we found out that they depend upon the magnitude of the error. Okay, not on whether it's in the numerator or denominator. Okay. So that's how there are errors in the slope and in the F plot. So now to overcome this issue, what they do is they use what is known as a dual slope voltmeter. So in the dual slope voltmeter, what happens is there's an integrator, okay? There's an integrator which has some constant C something, and there's a switch. It gets connected either to your input or to some minus VR. Okay, some reference value, reference voltage which we know. That goes to your integrator. That is compared with some zero value. And then that goes again to your AND gate. Again, we have an F clock. And this goes again to your counter. Okay. So now, how does this work? So suppose at time there's a time t0. Okay. This is my Vy, let us assume Vy. This is my time t0. At time t0, this is a plot of Vy. At time t0, Vy value is 0. Okay, it is 0. Then when what will happen is Vin will be connected. Vin will be connected. So it will increase it will increase like this. Okay, it will increase like this. And it will reach some value. So this is a time t1. Then at this time t1, what will happen? This will get disconnected. Okay. And this will get connected. Then this will reduce. Will reduce. This is T2. Okay. So for this period of time, Vin was connected. For this period of time, minus VR was connected. Okay. And initially the value was 0. Finally, again it reaches 0. So now, this is time. So now how will this change? What is this slope? This slope actually is given by B in upon T1. No. Sorry. This will reach, sorry, let me just move it. This is my Vy voltage. It will reach a maximum value, which is given by V in into T1. Okay, because it is an integrator. So an integrator will increase the value. So suppose let us say your Vy is equal to integration from 0 to T1 V in into dt. Okay. So what it will be V in into T from 0 to T1. So that is why your Vy is equal to V in into T1. Okay. This is Vy is equal to V in into T1. So that is basically what your integrator is doing. So your Vy at time T1 is equal to V in into T1. Now, we have assumed that the constant of integration of your integrator is 1. Let us assume that for the time being. Now, okay, we need that constant of integration actually. There's a constant of integration C. So what will be the output of your integrator? Will actually be C integration of V in into of V in. Okay, from 0 to T1. So it will be C into V in of T from 0 to T1. So this C into V in into T1. So Vy will be C into V in into T1. Okay. This is your Vy at time T1. We have found it to be C into V in into T1. Now what happens? V in is disconnected. And what is connected? Minus Vr is connected. Vr is some voltage which we know. Accurately, it is connected. We know. So what happens? Your Vy of T will be equal to C integration from what time? It is starting from T1 to some value T. What's the voltage? Minus Vr into dt plus Vy of T1. Because this is the initial condition. Okay, this is the initial condition of your integrator. This has to be included. In the previous case, it didn't need to be included because the initial condition was 0. This was your initial condition. So I could neglect it. I did not, it is there. Okay. This also is your initial condition. So now the Vy of T is equal to minus C into Vr integration of dt from T1 into T plus Vy of T1. I go to the next page. So your Vy of T is equal to minus C Vr T from T1 to T plus Vy of T1. What is Vy of T1? Is C into V in into T1. So that is C into V in into T1. Now your Vy at T2 is equal to what? Vy at T2 is equal to 0. Okay, at time T2 it is equal to 0. So Vy of T2 is equal to 0. So 0 is equal to minus C into Vr T2 minus T1 plus C into V in into T1. So C into Vr upon T2 minus T1 is equal to C into V in into T1. Therefore, V in is equal to Vr into T2 minus T1 upon V in into T1. Because this C and C gets cancelled. Okay. So I hope this derivation is clear. So we get V in is equal to Vr into T2 minus T1 upon V in into T1. This is my derivation of my voltage. Now, how do we measure T2 and T1? T1 and T2, they are measured using your counter. Okay. So this T1 is equal to N1 into F clock, right? Sorry, it is N1 upon f clock. So your counter started from 0, and then after time t1, it reaches what? It reaches n1. Okay. So here, what is the counter value? It was 0. Now it reached n1. Here it reached n2. And what is the t2? T2 is equal to n2 upon f clock. So now we will substitute over here. So we have Vin is equal to VR into n2 upon f clock minus n1 upon f clock upon Vin into n1 upon f clock. So your Vin, sorry, this Vin will not be here. Okay. So your Vn is equal to Vr into n2 minus n1 upon n1. Okay. So in this manner, your input voltage, this is independent of C and F clock. Okay, it is independent of C and F clock. So even if your C will change, even if this C changes, even if this C changes, or even if your F clock will change, your output which you measure will be accurate. Any doubts? So this is the advantage of the dual slope voltmeter. Do you want me to repeat anything? Okay, if there are no doubts, I'll proceed further. So there is something known as a digital ramp type voltmeter. Okay. So what it does is, it is similar to this. It is similar to this. So before that, I will start what is known as a DAC. So DAC is what? It is a digital to analog converter. So basically, it is a kind of data converter. It converts some digital value to an analog value. Now, in real life or in many situations, the signal, like your voice, your sound, the temperature, all these are actual real world signals are analog. Okay, they are analog. But when we are using what is known as a computer, a mobile, or a microcontroller, or FPGA, etc., they are digital. They require digital value. So what this there is something known as a ADC, which will convert an analog value to a digital value. Okay, that is an analog to digital converter. Next, your computer will do all sorts of processing, etc. and tell you that this is the voltage. Now it should be shown in some screen or somewhere. So it will be put in a number. It will show 48 point something, okay, or some value. So you have to output that value, that voltage or something. So then you will use a DAC, that is a digital to analog converter. Okay. So now let us consider a 3-bit ADC, 3-bit DAC. Okay, there's a 3-bit DAC. This is my DAC. Okay, it has 3 bits. So there's a D0 bit, D1 bit, D2 bit. D2 is the MSB, D0 is the LSB, and this is the output. Okay, and it has something known as V resolution. We will come to that later. So now this is my D2, D1, D0, this is my V out. So if all are zeros, then in digital what it means? It is 0 and V out will be 0. If it is like this, in digital it means 1. So this will be 1 into V resolution. If it comes like this, it will be 2 into V resolution. If it comes like this, that means 3. This 3 into V resolution. Okay. If it looks like this, means 4. It is 4 into V resolution. If it is like this, means 5 into V resolution. 6 into V resolution. This is 7 into V resolution. Okay. So this is the output of your DAC. This is the output of your DAC. So initially it is, when all are zeros, it is 0. And as it is incremented, it becomes V res 2 into V resolution, 3 into V resolution, 4 into V resolution, etc. So this is the output of your DAC. Okay. Now, this can be from my counter. This can come from my counter. Okay. This D2, D1, D0 can come from a counter. Okay. This is a 3-bit counter and it has some clock, right? It has some clock. So when the clock comes, they get incremented accordingly. So, so when the clock comes, first initially it all are zeros. Then a clock comes, it becomes 1. This is 1, this becomes Venus. Next clock comes, it becomes 0, 1, 0, this 2 and 2 into Venus. So in this way, the DAC can generate what kind of pattern? It will generate like this pattern. Zero, 1, 2, 3, 4, 5, 6, 7. Okay. This all happens at the clock. Clock, another clock comes, clock. So at the clock event, and then this finally goes back to 0. Okay. So this is my F clock. This is my V output of my DAC. And this magnitude is V resolution. Okay, so this is our DAC will generate an output. Any queries in this part? Okay. So this is my voltage Vx, which I have to measure. And this is some we compare something which is coming. Okay. This goes to your AND gate, F clock. This goes to your counter. And these are digital things goes to your DAC, which has also some V resolution. And that goes as your compare. So in the previous case over here, in this linear ramp type voltmeter, this VR was this slope, Now in this case, what will we have? We will have like this slope. Instead of a linear slope, I'm going to have a stairway slope. Okay. And then this will be something of my Vx. Let's say this is my Vx and this is my VR. So when when VR becomes greater than Vx, then what will happen? Then your counter is disabled. Okay. So your counter will count 0, 1, 2, 3, 4. So your counter will count the value 4. After it becomes low, your counter will become disabled. Okay. And it will hold on to the value 4. Then what you can say, your Vx is equal to 4 into V resolution. Okay. That is how we work with this digital ramp type voltmeter. Okay. So how much? Let us go to next page. So basically, this is like comparing voltage and generating some counter number, some counter value, right? So your counter value is always some integer, some discrete value. So basically, you are actually working as a ADC. You're actually converting some analog value to a digital value. Okay, it is a crude way of doing it, but it is like one way. You're converting an analog value to a digital value. Hmm. So basically, it is an analog to digital converter. Because your counter will only have some 0, 1, 1, 1, 0, something like this value. So this is a digital value, right? So using this measurement, you are getting an actual digital value. So your analog value is being converted to some digital value. Okay, so that's how this is analog and this is digital. Okay, so basically this is like kind of like an analog to digital converter. Hmm. So uh, I'll proceed further. I'll start with the successive approximation register ADC, SAR ADC. Okay, this works on the binary search algorithm. So in the previous case, suppose your Vx was, let us say, some 20. So what are you doing? You're starting from 0 and you're checking. This is your VR, okay? You're checking if your Vx is less than VR. If not, you're making it more. So you're making it 1, then you're making it 2, then you're making it 3, then you're making it 4, then you're making it 5, then you're making it 6, and it goes on. And it will take how much time? It will take 20. At 20, you will get the value. You will get the value. Yeah, at 20, you will get the value. So it is taking the number of cycles is 20. But if your Vx was, let us say, 1000, so then you'll have to count 1000 times. Okay. Let us say your Vx is 1023. Then you'll have to count till 1023 times, etc. Something like this you have to do. So this is a very boring thing. Like you're told to say that the weight or the number is like say 550, but you will start from 0 and 550. You'll compare, then you compare 1 and 550, 2 and 550, 3 and 550, so on. You will go and compare. So it is like a waste of time. Okay, it's a waste of time. Another thing I'd like to point out over here is this depends on the bits. Okay, how many bits are there? So this is a 3-bit DAC I consider, example of 3-bit DAC. So 3-bit DAC will count from 0 to 7. Okay. So if I have to count till 1023, then I require a 10-bit DAC. Okay, a 10-bit DAC. It requires 10 bits. Okay. So this is like a 10-bit DAC was required. Okay, 10 bits we have to count. So the number of for a n-bit ADC, the number of counts required was 2 raised to n, which is very large. Okay, so in computer science, there's something known as O complexity. So big O complexity, big O notation is there. So it is very, very complex. It is very computationally intensive. It requires a lot of computation. So can we find a way in which we can minimize the number of computations, but we can actually accurately and fast find the value? Okay. So what we will do in this case is, suppose this my 0 and this my Vmax. Okay. This is my Vmax by 2 point. Now let us say my voltage is okay. So this is the range of my ADC. Okay, the range of the ADC. It is from 0 to Vmax. Okay, now there's a point known as Vmax by 2. So what I will do is, I will first check, is it, what is my Vx? Is my Vx greater than Vmax by 2? If it comes out to be false, okay, if it comes out to be false, then what does it mean? My voltage is in this range. So that means I have to focus on this range. So then I will change the focus. My focus range will then become 0 to Vmax by 2. So I know my Vx is within this range. Then I will check between Vmax by 4. So I will check, is my Vx greater than Vmax by 4? If it comes out to be true, then I know my voltage is in this range, right? So then what will I do? I will consider range, this range, Vmax by 4 and Vmax by 2. Then I'll consider the midpoint of that, that is 3 by 4 Vmax. Then I will check, is my voltage Vx greater than 3 by 4 Vmax? And if it comes out to be false, okay, that means it is not in this range. That means it is actually in this range, right? It is not in this range, it is in this range. So now I have to focus now on what? Vmax by 4 and 3 by 4 Vmax. Okay. So now, what is the mean of this? Sorry, this is not 3 by 4 Vmax. This will be, this actually is 3 by 8 Vmax. Okay, this actually is 3 by 8 Vmax. So this will actually be 5/8 V max. Okay. So then I have to check again in which range. So in this way, what I'm doing is I'm narrowing the range. I am narrowing the range, and then I will determine what is the applied voltage. Okay, then I will determine what is the applied voltage. So first I will check, is it greater than Vmax by 2? Then I will know in which range it is. If it is greater than Vmax by 2, then it is in this range. Otherwise, it will be in this range. Huh. Then I will go to the next range where it is actually. And then I'll again consider the midpoint of that range. And then I will compare with that midpoint. And then I will finally find out at which range. And then I will slowly converge to the actual value. Okay, so I'm narrowing the range and I'm converging to the actual value. So this is how the SAR ADC works. This is how the SAR ADC works. This is how the SAR voltmeter works. Okay, it is successively approximate and it will give you your estimate. Okay. Next, so how many cycles does this need? Suppose there's an n bit SAR ADC, then it will require n number of cycles. It will require n cycles. So in the previous case, it required 2 raised to n cycles, which is very large. But in this case, it requires only n cycles. Okay, it will require only n cycles it requires. So now we have to consider something else that is known as a flash ADC. So flash ADC, you can remember it is like the fastest ADC. Okay, to the ADCs which we have considered. So in that, what it does is there's a VREF, there's R, let us consider for 2-bit case R, and R. And this is your ground. So at this point, what will be the potential? At this point, what will be my potential? What will be the voltage? No, all the R's are same, right? Because all the R's are same, at this point, the potential will be VREF by 4. Hmm. So at this point, it is VREF by 2. At this point, it is 3/4 VREF. Okay. So what I will do then is I will compare all these voltages with what is known as a comparator. Okay, there's a minus, 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 the plus, 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 and all these are connected to my Vx. That is the unknown voltage which I want to measure. Okay. So if my Vx, suppose my Vx, if my Vx is 0.6 VREF, okay, my Vx is 0.6 VREF. What does it mean? what will be the output of this one? What will be the output of this? Can you tell me? If my Vx is equal to 0.6 Vref, what will be the output of this comparator? Vx is plus and minus. So it is comparing 0.6 Vref and ground. So if at the plus terminal it is 0.6 Vref and at the negative terminal it is ground, what will be the output of the comparator? Will it be 1 positive or high, or will it be 0 low? It will be 1. So this will be 1. Similarly, over here, what will be the output? Here I'm comparing 0.25 Vref, 0.25 Vref and 0.6 Vref. So what will be the output? Yeah, it will be high. So here it is high. What will be over here? Here also it should be high. Okay. Over here, what it will be? It is 0.6 Vref here. It is point. It is your Vx is coming here and 0.5 Vref. So it is comparing 0.6 Vref at the positive and 0.5 Vref over here. So what will be the output? It will be high over here also. Over here, what will be the output? Because you're comparing 0.6 Vref and minus 0.75 Vref. So what should be the output? It will be low. It should be 0. Okay, it is 0. Now, what do you want? What do you want? We want it to be there will be some sort of uh, digital logic converter. There will be some digital logic which will convert it into 3 bits. Okay, this is your D2 bit. So first of all, this is a 2-bit ADC, so it will be 2 bits. Okay, so it will be your D1 and D0. So this should be mapped to some value. Let us say it should be actually 0 and 1, because let us say this is your Vx and this your it is this is your D1 and D0. So if your Vx is 0.25, then this will be how much? Your Vx is between 0 to Vx to 0.25. You want it to be 0, 0. If it is between 0.25 Vx and 0.5, you want it to be 0 and 1. If you want it and between 0.5 Vx to 0.75, it will be 1, 0. 0.75 Vx into 1, it will be 1, 1. Okay. This is your input voltage. But now you are getting this value 0, 1, 1, 1. So this 0, 1, 1, 1 has to be converted by digital logic to give you this D1, D0. Okay. Those are known as some bubble codes or something, which is just mapping it from this comparator output, the comparator output to the actual digital output. Hmm. Okay. So can you tell me how many cycles are required for this? How many times do I need to compare? Okay. First question is how many comparators are required? How many comparators are there in this circuit? 4. And it is a 2-bit ADC, right? So the number of comparators required for an n-bit flash ADC the number of comparators required is 2 raised to n. Okay, 2 raised to n. And how many cycles is it taking to convert? Hmm? Here, how many cycles is it taking to convert? Yeah, 1 cycle. Okay, 1 cycle it is taking to convert. Right? So basically, what has happened is in the SAR ADC, we were using only one comparator. We were using only one comparator. So we were taking n cycles to compare. So we will first give some value, some voltage, and then we will compare with that. Right? Then we will change that voltage to some other voltage and we will compare. So but we will use only one comparator. But in this case, instead of changing those voltages, we give those reference voltages and we have large number of comparators. So they do that comparison at a time. At one instant, they do all the comparisons at one shot and then they give you what is your digital output. So that is why the flash ADC is the fastest ADC. But it requires a lot of comparators. So it becomes very expensive as well as it will consume a lot of power as well. Okay. So, clear any questions? So now we'll go to next topic, which is DAC. That is digital to analog converter. Okay. So, as I said, we will give some binary data, binary digital value, and your DAC will convert it into some analog value. It will have some resolution. So now we will see what circuit we can use to get that. So before that, we will consider this case. I have a resistor R here. I have a resistor R here. This is with respect to ground. So what is the effective resistance from here to here? How much is the resistance? If I use a multimeter, how much resistance will read? 2R. Okay, it will read 2R. Now, what I do is, I will connect another resistance here, 2R. Then what resistance it will show? From this point to the ground. It will give resistance R. So in this fashion, we make a network. Okay. Let me proceed. Now, if I apply some voltage over here, let us say I apply voltage V reference. Okay. So what will be the resistance seen over here? So between this point to this point, it is 2R. 2R parallel 2R becomes R. Then this resistance R plus R becomes 2R, which is again in parallel to 2R. So it becomes effectively over here also resistance is R. Then this R plus R becomes 2R parallel to 2R. So the effective resistance over here is again R. Okay. Yes. So the effective resistance seen as R. So here the current will be V ref by R. Okay. So that is, let us say that is your I ref. So now when this current comes over here, it has two paths. It can either go here or go here. So how will it go? How much current will go where? Current I ref is flowing here, right? There are two paths now. So how, which path will it go? Will they get equally divided, or only, or will current flow only through one branch? Or in which proportion do they get divided? Let us consider from this point to this point. Yes. So from this point to this point, the resistance is actually 2R. And from this point to this point again, or here, wherever, it is again, it is 2R. So current gets divided. So it becomes I ref by 2. Here also current goes I ref by 2. Similar concept over here. Two R. Here again, the current becomes I ref by 4. And this again is I ref upon 4. Similarly, here it becomes I ref by 8. Here it becomes I ref by 8. Okay. So this is how these currents are divided. Now, what we do is, instead of connecting it to the ground, okay, instead of connecting it to the ground, this one point, there are two options. Can be connected either to ground or to some other point which voltage is very close to the ground. Let us name this point Vy. Okay. This point Vy is connected, or it gets connected like this over here. Let me draw it. Let's call this point. This all is the same point, right? And it can be moved. There can be a switch which can move it either here or here. It can be moved at any side. Okay. It can be moved on both the sides. It can either be connected here or here. Okay. Let us call the switch D0, D1, D2, D3. Okay. There was a mistake. Oh, sorry. Okay. Now this point has to be connected to your ground. So how do we connect it to ground? We connect it over here. And this we will connect. This is an R. Or some R1. And this is your V out. Okay. So there is, first of all, there is negative feedback. Right? So that means your virtual shorting concept is valid. Okay. So that means this point Vn and Vp. So your Vn is equal to Vp is equal to 0. Okay. This is confirmed. Now, what is this current which will flow here? There's some current which will flow here. Huh? That current depends whether this is connected or disconnected. So let us say that if D1 is equal to 0, means it is connected to the ground. If D1 is equal to 1, means it is connected to Vn. Okay. So your current I actually is D2 into Iref by 2 plus D1 into Iref by 4 plus D0 into Iref by 8. Okay. So this is a current I which is flowing. Now what is your V output? Your V output is equal to 0 minus I into R. Right? So that is equal to your minus or minus R1. Okay, the minus R1 to D1 by 2 Iref, D2 by 2 Iref plus D1 Iref by 4 plus D0 Iref by 8. So that is, sorry, your V0 is equal to minus R1 Iref by 8 into 2 raised to 2 D1 D2 plus 2 raised to 1 D1 plus D0. Okay. Your Iref is what? Vref by R. Your V0 is equal to minus R1 Vref by 8R 2 raised to 2 D2 plus 2 raised to 1 D0 plus 2 raised to 0 D0. Okay. So this is my output. So now let us put my D2 is equal to 1 and D0 is equal to 1 and my D1 is equal to 0. Then what will be my V output? Can you tell me? Yeah. So it will be minus R1 Vref by R upon 8 into 5. Okay. So this is how, depending on this digital number which is there, D2, D0, D1, they will be like switches. Okay. They are controlled by some logic, etc. So that logic will decide whether it is connected to the ground or connected to Vn. Okay. Based on that, we will get a particular voltage. So this is how we can generate the voltage we want by just opening or closing switches, depending on some digital number. Okay, that is why this is known as a digital to analog converter. And this is known as an R to R ladder. This is the R to R ladder logic. Okay. Yeah. Thank you. So this is my resolution. So I can change my output only in steps of this. My output can only be 0 or minus R1 Vref by 8R or into 2 or into 3 or into 4. But this is a common factor. So this is my resolution of my DAC. Okay. So we will check another type of circuit. DAC using adder circuit. Okay. Again, we have a op-amp. Now we have some resistors, let us say R0, R1, R2. All are connected to some same point, some Vref. Okay. And this all are connected to the same point. Only there are switches. Switches. D0, D1, D2. Okay. This is some R. This is your V output. So now, depending on D0, D1, D2, it gets connected or disconnected. Suppose they were all connected. Just assume that they were all connected. So, what do we have? We have Vref minus 0 upon R2 into D2 plus Vref minus 0 to R1 is will be your D2, D1 plus D0 into Vref minus 0 upon R0. This is your current I, right? Is equal to I. And what is your V0? Your V0 is equal to minus I into R. So your V0 is actually minus R upon D2 Vref by R2 plus D1 Vref by R1 plus D0 Vref by R0. What do we do is we make R to be equal to, sorry, we make R0 is equal to 8R. R1 is equal to 4R. R2 is equal to 2R. So we get V0 is equal to minus R upon R into D2 Vref by 2 plus D1 Vref by 4 plus D0 Vref by 8. So that makes your V0 to be equal to minus Vref upon D2 by 2 plus D1 by 4 plus D0 by 8. Okay. Or your V0 is equal to minus Vref upon 8 into 2 raised to 2 D2 plus 2 raised to 1 D1 plus 2 raised to 0 D0. Okay. So again, by setting suitable values of D2, D1, D0, I can get an analog value. I can get an analog voltage. Any queries? Okay. So now we can start solving sums. Start this sum. Okay. So this question is about a dual slope ADC. Dual slope ADC or dual slope voltmeter? So we have this question over here. So first I will write what is given. My F clock is given to be 5 kilohertz. My N1 is known to be 2000 clock cycles. My N2 is found out to be 190 cycles. Okay. So, and my reference voltage Vref is equal to 4 volt. Well, let me write what they are saying. My integration time is 2000 cycles. My de-integration time is equal to 190 cycles. Okay. So what is a dual slope voltmeter? We have this integrator, right? It is either connected to my, sorry, it is either connected to your input or it is connected to your minus V reference. Okay. Initially, it is first connected to your input. And then what will happen? It will start rising, right? And then this is for your period of some time. So this is known as your integration time. And then it is connected to your minus VDEF and it comes back to 0. So this is known as your de-integration time. Okay. So now let us assume this as a slope. So it reaches the maximum, that is V peak. So your V peak, let us say this is some time which we have considered T1, de-integration time. So this from here to here is T1, de-integration time, this T2. So this actually is T2 minus T1. Okay. Because I'm counting it from 0, this is your time T1, this is your time T2. So this time is actually T2 minus T1. Is this particular time. So integration time is T1 and it reaches some, the slope of this will be equal to C into Vn upon T1. Okay. So your V peak, there's no upon T1. So your V peak is equal to C into Vn into T1. And this slope is actually minus C into Vr. And then it will reduce. At that slope, it will reduce. So now, it will go from V peak minus C Vr into T2 minus T1. So we have derived it earlier also. So your Vr actually is C into so your CVR into T2 minus T1 is equal to C into Vn into T1. So your Vn is equal to Vr into T2 minus T1 upon T1. So this is actually Vr into your de-integration time upon your integration time. So that is equal, what is your Vr? Is 4 into what is your de-integration time? 2000 cycles. De-integration time is 190 cycles and your integration time is 1000 cycles. That is equal to 4 into 190 upon 2000. So calculate and tell me how much is this? Okay, it comes out to be 0.38, it seems. Yeah. So this in volt. Okay. 0.38 volts. So basically we have to know, we have to understand what is the integration time, what is the de-integration time. And in the question, sir has provided like what is the integration time? When the integrator is connected to the unknown voltage, unknown input voltage. What is your de-integration time? When the reference voltage is connected, one thing you must note down is it will be minus V reference is connected, not just V reference. So once you know that logic, then you can derive what expression is there, and then you will get what is your V input. Okay. So now we will go to the next part of the question. Okay. They are saying to find the measurement resolution in millivolt of this voltmeter. Okay, we have to find the measurement resolution. So what is resolution? It is the smallest unit which it can measure. So what is the smallest unit it can measure? The resolution is equal to VR upon your integration time into 1. Okay, your V input could cause it to be 1 or 2 or 3 or 4 or 5, but the minimum it can measure is into 1, right? So that is why that is your resolution. And that is given by 4 upon 2000. So what is the value in volt over here? Millivolt, correct. That is why it is equal to 2 millivolt. Okay. Then the next part of the question is saying if the 5 kilohertz clock, driving clock, slows down by 8% due to aging, then how much error in percentage will be introduced in the meter reading? Okay. So they are saying F clock, which was initially 5 kilohertz, okay, slows down by 8%. So that was 5 kilohertz into 1 minus 0.08. Okay. So actually it becomes 5 into 0.92 kilohertz. So your F clock has reduced. Okay, your F clock has reduced. Then what will happen is your integration time previously, your nominal integration time was how much? It was 2000 into your F clock. Okay, it was 2000 into F clock. That will change. Okay, your nominal integration time was 2000 F clock. Your F clock has changed. So your integration time will change because you have told that for 2000 cycles you have to give your connector input and your F clock will change accordingly and your counter will reach the maximum value of 2000 and then you will disconnect it from your input and you will connect it to your reference. Then your de-integration time will also change. De-integration time will also change accordingly. Okay. So we know our integration time was what? It was given by T2 minus T1. And my integration time was T1. Okay. So now my T1, my T1 is dependent upon the number of clock cycles. And that is also given by 2000. I was told that it will count to 2000. Now, if my clock cycle frequency has changed, my de-integration time will change accordingly in such a manner that it has to come from here to here to here. It will be reducing, right? It will be reducing during the de-integration time. So your clock cycles are still coming. These are the clock cycles which are still being applied, right? So because the clock is reduced, the number of cycles which it will show will also reduce. This also will reduce. Let us say this was coming like this. Like this is my clock. Okay. This is my clock and this is my clock. Now I have told it that this will be equal to 2000. 2000 clock cycles it will go and it will go. It will increase. In one case, it will take 2000 cycles. Then in my other case, in the actual case when there's an error, what will happen is when there's an error, okay, the error is what? It has become slower. That means it will take more time. It will take more time. So this will keep on counting in such a way that this becomes 2000. Okay. So, and it will keep on going. This is slow clock, right? The clock is slow. So what will happen over here is this will instead go like this, and reach over here. It will reach here, and then it will further reduce. Okay. So you will notice that if your this is your N1, okay, this also, which you will count, that will also remain your N2. Both cases, it will be the same. Okay. So this is the advantage of the dual stroke case. And so your error, percentage error, will be 0. The error will remain 0. Hmm. Okay. So any queries in this? If there are no queries, I'll go to the next question. Okay. Oh, okay. Sorry. Okay, you're getting disconnected and connected. So I will share with you my Drive link and my YouTube link. So in the Drive link, all these notes I will upload, so which you can access. YouTube link is where I will record this recorded video. I will upload this video. Okay. So even you are getting disconnected or connected. Okay. Actually, the error part, let me repeat it. Okay. So now, in the normal case, it is taking 2000 cycles. This is my 2000 cycles it is taking. The clock 2000 cycles, it is reaching the maximum, and then it is reducing. Okay. In the next case, your clock has become slower. It has become slower because your clock has become slower. It will be your V input will be connected for more time, so it will reach a higher peak. Okay, it will reach a higher peak, and then it will take more time to reach the bottom. But what has happened is your clock is slow anyway. Your clock also has reduced. So the number of clock cycles it takes N2 to count in the normal case, as well as in this case, N2 will remain the same. So because the slope and the clock cycles is changed accordingly, the clock, although it has changed, the number of cycles which is there remains the same. That is why the error is 0. Okay. Hmm. Go to next question. So this is a single slope ADC. Okay, single slope ADC. So like a ramp type ADC. V peak of the ramp is 5 volt, and the number of bits is 10, and the clock is 20 kilohertz clock. Okay, they're asking estimate the maximum value of the input voltage that can be converted, as well as estimate the resolution of this ADC in millivolts, and estimate the maximum time and the ramp rate. Okay, there are many things they're asking. They're asking what is the Vmax which it can measure. Okay, what is the resolution? How much is the time for conversion, as well as what is the ramp rate? Okay, this can have a peak between 0 to 5 volt, right? So it can measure any input voltage between 0 to 5 volts. So the maximum it can measure, the V max which it can measure is 5 volt. Okay. The ramp is increasing from 0 to 5 volt. So in between 0 to 5 volt, any voltage which is there, it can measure it. So that is why the maximum voltage it can measure is 5 volt. This is done. Next, it will not be a linear thing. It will actually be in this small case. It will be like this. Like this will be the actual way it will increase. Okay. It will increase in this manner. In small steps, this ramp will increase. Okay. So what will be this finite small value which it can measure? So first let us see how much, because it is a 10 bits. 10 bits, maximum is 2 raised to 10. 2 raised to 10 is 1024. It can count maximum to 1024. So one small thing will actually be, the small thing is your resolution. Your resolution is what? Your V peak upon the maximum count, that is equal to 5 by 1024. So how much is that? Okay. So that will be 4.88 millivolt. Okay. Now what is the time for conversion? Your time, maximum time it will take to convert is equal to how much time it will count? 1024. So it will count from 0, 1, 2, 3, like that. And that happens at a frequency of f clock. So your time, the time it takes to convert, because it comes like this, then like this, then like this, right? Is equal to the maximum count upon the f clock. That is your 1024 upon your f clock is 20 kilohertz. So how much is this? Time in milliseconds. Yeah. So that will be equal to 51.2 milliseconds. Okay. Then, so this is your P conversion. Okay. And this is your V peak. So what is your ramp rate? Your ramp rate is the slope of this, right? So what is your slope given by? Your slope will be equal to this V peak minus 0, this point to this point, upon how much time? P conversion minus 0. So your slope, which is equal to your ramp rate, which is your V peak is 5 volt, divided by 51.2 milliseconds. So how much is that in volt per second? Yes. So it is 97.65 volt per second. Hmm. So this is how we have solved that question for the single slope ADC. We will go to the next question. Hmm. This is a SAR ADC. Number of bits is 20. F clock is 4 kilohertz. Okay. So now, how much, how long in millisecond does this ADC require to convert an input voltage? So we will consider worst case scenario. So worst case scenario is that it will take n cycles. Successive approximation, let's say ADC we told, right? Between 0 to max, it will or V peak. Right? This will be your V peak by 2. It will check in which range it is there. Like that, it will go on iteratively. So it will do it for n cycles. So your time, which it requires to convert, will be equal to your time for your clock into the into your ADC bits. Okay, into the bits and bits of the ADC. Okay. What is your T clock? It is 1 upon F clock into 20. So this 20 divided by 4 kilohertz, that is 5 milliseconds. Yes, correct. Okay. So this is for the successive approximation register ADC. Now you will check another question. So it asks how many comparators are required for 16-bit flash ADC. First thing we note down it is flash ADC, right? And the number of bits n is 16. So now in a flash bit ADC, the number of comparators is 2 raised to n minus 1. So that is how much? 2 raised to 16 minus 1. So how much is that? Yes. So it becomes 65,000. Let me ask another question. Suppose the clock was, let us say, 1 megahertz. So how much time will it take to give me the result? How much time will it take? Yes, it will take 1 upon f clock, 1 microsecond. Okay. So it is so fast. Just requires one cycle. Only one cycle is required for this, for the flash ADC. Now we will go to the last question. They are saying there are different types of ADCs according to the conversion speed, starting from the fastest ADC to the slowest ADC. So let us say we have studied three types of ADC. One is the digital ramp type ADC. Second is the successive approximation register type ADC. Third is the flash ADC. Okay. Let us check how many cycles are required. Suppose there are n-bit ADCs. Okay. N-bit ADCs. So how many cycles are required for this? For the digital RAM type ADC, how many cycles are required? 2 raised to n. 2 raised to n cycles are required. But how many comparators do I need in this case? How many comparators do I need? I require only one comparator. In the SAR ADC, how many cycles are required? I require n cycles. And again, I require one comparator. And in the flash ADC, how many cycles are required? I require one cycle, but now I need 2 raised to n comparators. Okay. So now you can see like which is the fastest. This is your fastest. Okay. This will determine your speed. Okay. This is the fastest. So, and this is more number of comparators means more cost. Okay. Which is more costly or etc. Which will consume more power and all. So this is the way. And the SAR ADC is the one which I have used. Okay. And in the microcontroller boards and all, which I have checked and all, SAR ADC is the one, both for the Texas Instruments as well as for the STM32 microcontroller, both use SAR ADC. Okay. So this is the case for the ADC. So we'll just have a brief recap what we did today. So first is a linear ramp type voltmeter. We are using comparators and op-amps. This is the comparator which is there. We are using an AND gate and we have a counter. So the counter must start from 0. And as long as your ramp is less than your Vx, your counter is enabled and it will count the number of clocks which come. And based on that, we will tell what is the value of Vx. But we found that this voltage Vx depends on your slope and depends on your clock. And if there is any change in your slope or in your clock, it will result in the change in the error. That will result in an error in your measurement. Okay. Hence, we want to avoid such a thing happening. So then we went for a dual slope voltmeter method. In this case, when we did the derivation, we found that the input voltage which is applied is dependent only on your reference voltage into this T2 minus T1 upon T1. Okay, which are all values of the counter. So it is independent of your clock. Okay, it is independent of your clock. Okay, so this depends on VR into N2 minus N1 upon N1. So what if we can make sure that my VR is fixed, it doesn't change, then I will get an accurate value. Okay, so now that is where these people are going for integrated circuits, etc. And there are various complexities. So now we have just given a basic overall top view to understand like how these systems work, how the ADC will work, how your DAC will work. They are just very superficial, ideal cases. Okay, when you go to an actual implementation of the IC, there will be many non-idealities will happen. Like how do you maintain this VR? VR will not always remain VR. It may change by 1%, 2%. The temperature changes, some other change happens. Then you must have some correction algorithm which will try, to maintain your VR, to regulate your VR at a fixed voltage. Okay. So all these things are quite complex, but we are just giving you a top overall knowledge so that you can understand how they work. Okay. So this is how using this method, we can get the output to be independent of the slope of your integrator and your F clock. Okay. So your integrator actually you will implement it using some circuit which is similar to this. Okay. So what is your V output? It is equal to minus V in upon RC into dt plus your V output initial condition. Okay, from 0 to t. Right? So your slope actually is equal to this minus 1 by RC, etc. Something like that. Okay, so even if this R will change, even if this R changes, even if this C changes, they may change their tolerance. Your resistance is not always 100 ohm. In your resistance, you have a tolerance band. So the tolerance band can be 1%, 2%, 5%. Your capacitor also value can change. So that means your slope will change. So your slope changes, then you're getting a wrong result. So to avoid that, the dual slope voltmeter, it will give a output which is independent of your slope. Okay, that is the power of the dual slope voltmeter. Okay. Then we also, what is a DAC? How do we generate DAC? How do we generate real world signals, etc.? So first I consider what is a DAC, how using D0, D1, DT. Your V out depends on the values of D0, D1, DT. Okay. These are like, binary digits. Okay. The normal format. So that if this digit is this much, then what is your digital value and what will be your output accordingly. So that I've shown. So this is basically like your counter. So if you have a counter which is giving D0 first like this, then D0 is changed, D1 also changes accordingly, then your output will become like a ramp, be a ramp. And in the earlier case, we compared with the straight line for the linear slope voltmeter. Now we will compare with this ramp. Okay, we will use this ramp. Okay, so some ramp like this will be added. So the ramp will have this change. So this is the minimum which it can measure. This minimum is known as your V resolution. Okay, that is known as your resolution. So all these concepts are used a lot in power electronics, digital control, etc., where these things matter. Okay, these things play a very significant role. So again, this counter, this DAC, this clock, compare. So all these are happening. Okay, all these are happening. Then, so this is like a very crude way. It takes a long time to get to the actual voltage which we need. But then we can use what is known as SAR ADC. Okay, it will do like a binary search algorithm method it uses. and it will check whether it is in this range or in this range. Then it says whether it's in this range or in this range. Then whether it's in this range or in this range. So this will narrow down where exactly you want, where exactly is your applied voltage. Okay. So that is why it takes n cycles for an n bit SAR ADC. Flash ADC is the fastest. It will give your input, it will give you what's your output. One cycle, it will give you your output. That's why it is very fast. So number of comparators are required a lot. So it is very powerful. It takes a lot of power. So what people do is they will use some bits, the higher number of bits they will use of flash ADC. For the remaining bits, they will use a SAR ADC. So they will use a combination of your SAR ADC and flash ADC and create a hybrid ADC. And that architecture they use to make it fast, as well as they will reduce the number of comparators which are required. Okay, so that's how they, like they try to optimize in all these industries, etc. They try to optimize. They will say that these many architectures, these many structures are there. So I will take the advantage of this structure and I take the advantage of this structure. I will combine them. I will see it in such a way that the architecture once disadvantage is there, but I will try to minimize the disadvantage as much as possible. And the architecture too, there's another disadvantage. But I will work with both the advantages and disadvantages and create a ADC which is fast as well as it takes lesser number of comparators. Okay, so that is how the industry will design your ADC and DAC. They will use a combination of these two architectures. Then there's a DAC, that is digital to analog converter. So one is the outward ladder mechanism which I showed. Next is the adder circuit which I showed. And one thing to note down in DAC is delay is very low, very small. So in your actual digital algorithm, it is your ADC. Your ADC which actually causes most of your delay. It is your ADC which is causing most of your delay. Your DAC will work very fast. This is your ADC which takes time to compare, to compute, to decide what is the digital value. But your DAC, just say these many bits should be high, the current will flow, it will give you your output. Okay, so your DAC is fast. There will be some delay, but that delay is negligible compared to the delay in your ADC. Okay. Then we check some questions. We check the question required regarding dual slope ADC. Then we check the question regarding your linear ramp type ADC. And then we considered for a SAR ADC, how much time it will take to convert. Flash ADC, we consider how many comparators are required. Then we made a comparison table of each type of ADC, and then we finished. Okay. I see voltage compatible. I didn't understand like these logics, these ADCs and DAC and this counter, etc. All these are work in a way to control your power electronics. Okay, to like how to run your power electronics means you need all these sort of ADC and DAC, etc. to and the counters to generate what duty ratio or what gate signal I must give to my converter, power electronics converter, so that it will run. Okay. So I'll give you one simple example. Let us consider voltage mode control. Okay, that is known as voltage mode control. Oh, okay. What I'm saying is maximum 15 volts. Acha, yes. I'll tell you. So now, let us say this is your power electronics converter. Okay, it has an output. Let us say your output is, let us say, 100 volt. Okay, we will use what is known as a resistive divider, R2, R1, etc. and bring this within the range, let us say 5 volt. Okay, this 5 volt signal goes to my ADC. It goes to my ADC. So this is my output voltage in terms of sense value that I will compare with certain reference voltage which I want. That will generate the error. That will go to my controller. Okay. Controller will generate some control voltage. That will be compared with my counter. There I have a counter which is generating some voltage. Okay. That goes over here. And this will generate what duty ratio I require, which will go over here. So this is your counter value and this is your vcon. So this will generate your duty ratio, which you must apply for your converter. Okay. So that is how this 100 volt which was there was stepped down such that it is compatible with your op-amp. Okay. So any other queries? Yeah. They are kept at a different range because your ADC cannot handle very high voltage. No, it should handle some low voltage. So your power electronic converter is like your power stage, your power circuit. But then it will be brought down, the signals will be brought down to a voltage which is low so that it can be used in your control circuit. So in your control circuit, you will bring the voltages low and that will go to your ADC and everything. Okay. And I forgot to put something. Here actually there will be your DAC or a DAC also can be there. In this case, DAC is not required because it is comparing. This is like a greater than or equal to. This is if it is, which one is greater? Sorry, which one is less? But in some cases, you will require a DAC also. Digital to analog conversion. In some control techniques. So all this entire part is digital. Okay. Then over here, there will actually be something known as a gate driver. And then, so that means this entire part is analog. This entire part is analog, this entire part is digital. So now to go from analog to digital, I need an ADC. Now this is a digital value, which through a gate driver is something which will generate an analog signal. Okay, that's a different. Any other queries? Okay. Okay then. Thank you for joining.